Thank you for giving me the opportunity to share my research in this seminar. I am Melanie Siegburg, and I did my PhD project about the evolution of faulting and magmatism during volcanic rifting, which I looked in detail at the Bosse-Berisha volcanic complex in the N.Main Ethiopian Rift. This project was a multidisciplinary approach linking mapping, geochemistry, geochronology, and structural geology. Here I would like to present the structural geology part. The availability of high resolution, remote sampling data, absolute age constraints, argon-argon dating, and well-exposed normal faults gave me the unique possibility to quantify extension by faulting over a long period of time in tectonomagmatic segments. The study area is the northern N.Main Ethiopian Rift system, which is located in the northern part of the East African Rift. The N.Main Ethiopian Rift is divided into the southern, central, and northern part. In my study, I focus on the northern part of the N.Main Ethiopian Rift, which is thought to have been started rifting around 11 million years ago and was associated with volcanism on northeast striking waterfalls. Through time, extension and volcanism have become focused on the 20-kilometer wide right-stepping anechelon zone of magmatic segments. We now zoom into the northern N.Main Ethiopian Rift. The segments are defined by the density, distribution, orientation of faults, fissures, and craters and cones, and the alignment with the central silicic volcanic complex. They range between 40 and 70 kilometers in length. The spacing between the segments vary between 2 kilometers between the Bosse magmatic segment and Coney magmatic segments, as well as 18 kilometers between Gedemsa segment and Bosse magmatic segment. I mapped the faults of the segments and border regions and measured the orientation to constrain the rift geometry. The border faults on the western margin strike 30 to 50 kilometers from north, whereas the border faults on the eastern margin have more focused orientation between 43 and 45 degrees from north. Orientation of the segments vary between 25 degrees from north at Gedemsa and 18 degrees from north at Frontale segment. Using this orientation, the plate motion vector and the overall rift orientation, here the dashed line, I determined the rift geometry with the angles alpha and phi. The relation of these angles shown based on the method of Tackwell et al. 1996 if a rift is oblique, transtensional, or orthogonal. Even by using different plate motion vectors, the N.Main Ethiopian Rift indicates a transtensional kinematic with an increasing shear component northwards. The change of the shear component can be caused by purely tectonics, such as different influence of pre-existing cross-rift structures, or by different amount of magmatism. To determine in more detail the kinematic of a segment, I chose the Bosse magmatic segments, here marked in red, due to the availability of LiDAR data, age constraints, and previous mapping. Along this segment, I did field work and I mapped small-scale faults and fissures on top of the volcano, which can be seen here on the left-hand side, as well as large displacement faults towards the segment tips, which are here shown on the right-hand side. In addition, I measured the throw, heave, and opening of faults using profiles every 25 meters in LiDAR data and every 100 to 200 meters in ASTER data. These profiles, here marked in red, show different architecture of normal faults going to different lava units. The result of the fault displacement analysis is presented in this map. Here in the middle, You can see the volcanic edifice. In blue, faults dipping towards southeast, and in red, faults dipping towards northwest. The line thickness indicates the vertical displacement. The Bossard magmatic segment contains two main north-northeast, south-southwest orientated fault cluster zones, dipping towards each other and forming a 5-kilometer wide graben structure within the segment. This can be caused by multiple rifting events with different dike width and intrusion depth zones. Magmatism is presented by aligned fissures, cones, craters, and source of lava flows, here shown as black dots. Using a density analysis of volcanic activity, dark shades on this map, you can see that most volcanism happened along the central fault zone in the center of the segment, whereas the Bossard volcanic complex indicates the southern part of this active zone. A remnant caldera rim, here on this map, is aligned with the western fault zone and probably buried by younger lavas on the central fault zone. Magmatism suggests an asymmetry within the segment with dominant activity on the eastern side of the graben, which is similar to the overall rift asymmetry. Looking into more detail on the variation of vertical displacement over the segment, the throws range from 1 to 200 meters over a fault length of up to 15 kilometers. The central fault zone has throws of 20 to 80 meters in the north and up to 120 meters in the south. The western fault zone has displacement of up to 200 meters in the north, here shown by line thickness, and in the north and in the south, it's about maximum 140 meters. The western segment is dominantly active by tectonic activity. Between these two fault zones, distributed faults, for example, here on the map, in young lavas with low throws, link the two sides of the graben. These data show that towards the segment tips, the faults are more localized and have higher displacement and throw length ratios compared to the magmatic active segment center. Based on the quotient of throw and age, I calculated slip rates. They range from 0.012 to 0.15 millimeter per year at faults cutting through rift floor lavas, and 0.2 to 0.5 millimeter per year at faults cutting through quaternary lavas. A more detailed example of changing deformation and slip rates within different geological units is located in the southern part of the volcanic complex, here shown by this black box. If we zoom in here, you can see the black box is this map with on the left hand side, you can see the southern part. On the right hand side, you can see the northern part of this box. The fault network runs through the Nasrid pyroclastic unit, which is about 2.5 million years old, here marked in green. The Bofa basalt, which is about 300,000 years old, and the southern lava flows of the Bossard volcanic complex, where one of them is dated to 6,400 years. In the top diagram, the elevation is presented by the black line, and the sum of throws is presented by the gray line. In the diagram B and C, you can find the throw of individual faults. In the diagram D, the calculated slip rates of the sum of throws is presented. The slip rate range from 0.05 to 4.3 millimeter per year. They are very heterogeneous, show a 100-fold increase towards faults cutting through young lavas. The faults cutting through the Nasrid unit are likely activated shortly after the emplacement of the buffer basalts due to the similar displacement values, which would result in a slip rate of 0.43 millimeter per year. These slip rates are in the range of other slip rates from faults in the northern main Ethiopian Rift. However, there is a general lack of slip rates in this region, and because of this, it is hard to interpret the significance of these slip rates. The increase of slip rates towards younger lavas may indicate an increase of more active recent periods, or an averaging out over long time scales of active and inactive periods. As we can see on this example, faults are very close, they link to each other, and they interact. This fault linkage can be observed on different scales. We observed a large scale linkage between the two main fault zones in the segment by distributed faults, here shown on the left image, as well as towards segment tips. North-northeast faults propagate into northeast orientated faults and forming splay patterns, curved faults, and sigmoidal shapes. On a smaller scale, we observe many relay ramps in different stages of breaching, here shown on the right image. This suggests that fault linkage plays a significant role for the tectonic activity and fault growth in the segment. The contribution of the southern central fault zone to the overall rift extension can be calculated by comparing our results with geodetic measurements. Assuming a typical normal fault dip of 60 degrees from north at the surface and 45 degrees at depth, we calculated the heave of individual faults and summed over the fault system. The minimum extension is presented here in the table. As we know, most of the extension is focused on the magmatic segments, with an overall extension rate of 2 millimeters per year measured by GPS measurements. Assuming the same scenario over the last 300,000 years, we compute that the southern fault zone accumulates 5% of the overall extension at mastered pyroplastics and buffer basalt, and less than 50% at the flank of the southern volcanic edifice. This suggests a significant contribution to the overall rift extension in the last 6,000 years. The remaining extension can be caused by other rift valley faults not sampled and alternative modes of extension such as intrusions. I would like to conclude using this sketch. The orientation of rift segments relative to the overall rift orientation and plate motion vector indicate a transtensional kinematic with an increasing shear component towards north. The Bossett magmatic segment has two main north-northeast orientated fault zones, dipping towards each other and forming a 5-kilometer wide graben. Towards the segment tips, faults are more localized and have a higher displacement and throw length ratio. Slip rates increase towards younger lavas, suggesting a more active recent period or an averaging out over longer timescales, including active and inactive phases. Fault linkage is observed on different scales and plays a significant role for tectonic activity and fault growth. The fault network of the southern part of the central axis indicates a significant contribution to the overall rift extension in the last 6,400 years. Many thanks.